So in this video, I want to talk about what are known as contingency tables, and we'll do a hypothesis test example using a quote-unquote real-life example with contingency tables. And contingency tables are going to tie in heavily to just the chi-square test. So if you are unfamiliar with chi-square, definitely take a look at that one first, because I'm going to use some of the information and sort of the knowledge that you get from understanding chi-square. Okay, so what is a contingency table? Well, the idea is that data is classified by two different criteria, and each criterion with two or more columns. So I don't know, maybe I'll make an example. You could sort of you could have two different criterion. Maybe you classify your data into males and females, and then you can subclassify that further. Maybe you're interested in politics, and maybe you look at whether somebody's a Democrat or a Republican or independent. I know there's other parties, but whatever. Same thing, you could do counts. You could look at females, and you could maybe count, how many are Democrats, Republicans, or independents. So the idea is, again, you're just going to break it down into two categories, and then you're going to break it down into two or more categories, is the idea. So the idea is there's going to be something of interest, and the idea is we're going to try to figure out whether those categorical variables are independent or dependent. So does one affect the other, is intuitively the idea to me. Is there a relationship? And again, as I said, definitely make sure you take a look at chi-square first. Be familiar with that. And again, just a little definition, a mathematical definition of what it means for two events to be independent. And again, just a little intuitive idea. So intuitively, it means that event A occurring or not in no way affects whether event B will occur, and vice versa. That's an example of, that's what it means for events to be independent. So my classic example, I could look at the event A, whether or not it will rain today, and my other event B could be, if I flip a coin, what will happen, right? Whether it rains or not in no way affects what's going to happen if I flip a coin. Those two events are independent. Okay, so let's go over the formal stuff. Again, there's not a lot to do other than to talk about stuff, and then you'll see that the mathematics actually isn't that bad. So this is going to be the chi-square test of independence. So ultimately what we're interested in, we're going to do a hypothesis test. And the idea is our null hypothesis is that the two factors of interest are independent, or it means there's no association. And our null hypothesis, well, it's going to be that the two factors of interest are not independent. So yeah, there is some sort of association going on between those two events. And here's our formula. So this may look, you can see this chi-squared. Notice we have two summations now. Don't get thrown off by that notation. It just means somehow we're going to take into account all of our data. You'll see that in a second. This bottom notation, we're going to have to come up with what's known as expected counts. So we saw expected counts before. And we'll talk about how to compute those using that formula. So it's going to be very much the same. So the process that we're going to go through, the one that I'm going to use, so we're going to reject the null hypothesis if our test statistic, chi-squared, is greater than the value we get from chi-squared based on our level of significance, and our degrees of freedom. Okay, and you'll see that again. Maybe even let me put the alpha in there because I think it's good to emphasize that. And there's two rejection rules. I always like to use this first one, so that's the one you'll see me focus on. Well, just like chi-square, for contingency tables to go through this process, we need to make sure that our data are counts. They're not percentages or averages. We've just got some random sample of size n, and the sample size n is large enough to get an approximate chi-square distribution. And you may recall the big condition that we need to make sure of, just make sure the expected counts should be at least 5. That's kind of the thing that I look for in my table. I mean, of course, these other things are important too. Just you don't want the counts to be too small. If they are, either group them or discard them is the idea. Okay, so let's do our real life example here. And I think this is actually quite interesting because the one I'm going to use, it is based on a study that I heard about years ago. So it's interesting. But okay, let's again talk about this notion in general. What are we trying to do? So if we want to put it in a real setting, we could, one thing you may ask yourself, and it's certainly a common research thing, is, so a very common question is to ask whether or not a parent's behavior or their past actions is associated with a child's actions or behavior. So I used politics at the beginning. Do you think maybe a mom or a dad's or a parent's political views, do you think that would affect a child's views? My guess is it would. If mom or dad smokes, in this case, if dad smokes, what do you think about a particular child? Do you think that child would be more or less likely to smoke? Well, we could collect data and answer that. Again, I would say, yeah, probably so. But again, we could determine that. And the one that I'm actually going to use is, the question is a mother's education level associated with her daughter's feelings towards math? So this was a very interesting example to me just because, well, I like math, and it's an interesting question about women's views in mathematics, which is something I've read a bit about. So it's quite fascinating. Okay. Anyways, so we've got this real life example, right? We're trying to figure out. So we go out there and we collect some data. N equals 1,000. We've got, that's definitely right a big number, so that's good. We look at all these mother-daughter pairs and we start interviewing them. So we're going to take counts. I'm going to ask, mom what her education level is. And mom's education level could either have a high school degree, an undergraduate degree, or a graduate degree. I classify them into these into these three subcategories. And then I'm going to look at the daughter's opinion on math. Okay, so these are my two criteria that I've broken it down into, right? Like when I looked at the very beginning, I've got mom's education level. I've got mom's education level and the kid's feelings, right? And then based on that, we can sort of subclassify it. So if we look at mom's education level, right, there's three different things that can happen. She could have, again, a high school degree, undergrad, or graduate. And in this case, the daughter's opinions on math, I broke it down into three as well. She either hates it, she has no opinion on it, she's indifferent, or she really likes math, okay? So, and notice in this case, I've got 1, 2, 3 columns, and I've also got 1, 2, 3 rows. So suppose I go out there and I collect some data. I classify these 1,000 mom-daughter pairs. And it turns out of those 1,000 mom-daughter pairs, well, 120 of those mom-daughter pairs corresponded to mom having a high school degree and her daughter not liking math. And for example, if I look at maybe this value here, 140, that would correspond to, it says there's 140 mother-daughter pairs where mom has an undergraduate degree and her daughter loves math. And you can go through and look at those other values as well. And notice then I just have counts. So at the bottom of my high school, it says, if you look at the bottom rows, for example, it says there's 440, when I look at these mom-daughter pairs, 440 of those mom-daughter pairs corresponded to mom having a high school education, at most a high school education, for example. And if I look at this row total, 335, well, if I follow it over, it says out of those 1,000 mom-daughter pairs, 335 of those corresponded to where the daughter said she really loves math. So that's all those totals are in this case. And again, I've emphasized I've got the number of columns and the number of rows. Okay, so notice we haven't done much yet other than just interpret our contingency table. Okay, so this is what we're actually doing. So this is our hypothesis test. So let's state our null hypothesis and our alternative hypothesis. And they're basically pretty much always going to be this. Your null hypothesis is no association. So they're independent. So mom's education level in no way impacts how her daughter feels about math. And the alternative hypothesis is, well, yeah, depending on mom's education level, there is going to be a relationship between mom's education level and how her daughter feels about mathematics. That would be the alternative hypothesis. Notice the null hypothesis is always going to be no association. Okay. Or equivalently, we could say they're independent or not independent. So in this case, I did list, right? We had 3 rows and 3 columns. That's what we've got, a 3x3 contingency table. So 3 rows and 3 columns. So, 3 columns. That's going to help us compute our degrees of freedom. So what we do is we take, again, the number of rows. We take the number of rows minus 1 and multiply that by the number of columns minus 1. Minus 1. Okay, so that's how we get the degrees of freedom. So I had 3 rows, I subtract 1. I had 3 columns, I subtract 1. That'll give me 2 times 2, or 4. Now, at this point, again, we always pick some level of significance. A common level of significance is alpha equals 0.5, so let's just use that. So now this is where I've just got to, look up this value from a table. So we're looking up chi-squared. The value of 4, that just has to do with my degrees of freedom. And again, the number at the bottom, right, that just has to do with my value of alpha. And there's nothing to work for here. You just look up a table. So it says, okay, this is my significance level alpha. So it says we want alpha equals to 0.5. The degrees of freedom was equal to 4. And now I just look where those intersect. I'm getting 9.488, which, okay, we can round to 9.49. So again, there's nothing to do here. Just look at a table. Now, what do we do at this point? The only thing we have to do now, so now what? Now we just calculate our test statistic, and we just compare that value to this value we just found. That's all we have to do. Calculate this test statistic, we'll compare it, then we make a conclusion. So again, I haven't done much work yet. Okay, so now let's actually compute our test statistic. How do we do that? Well, just like with the chi-square, we're going to take observed values minus expected values. I think I left my square out there. Let's put that square on there because that's definitely important. So that's going to be our test statistic. Now, we have each of these values, right? This is going to be an observed value. So we've got all of these observed. We have 9 observed values. Now, the question is, how do we get the expected values? That's what I'm going to need. And to get the expected values, it says to get an expected count, we take a row total and multiply it. We take a row total and multiply it by a column total, and we divide that by the grand total. So let's do a couple examples, and then I'll just fill the rest of them in. Okay, so suppose I want to figure out the expected count. Based on my data, how many mom-daughter pairs would I expect to have at most a high school degree, and their daughter hates it? Well, it says what we do is we just look at that column total, and we look at that row total, and we multiply those two values together. So that's 225 times 440. And then we divide that by the grand total. There was 1,000 mom-daughter pairs that we interviewed. And when I multiplied this out, I got this to be exactly equal to 99.0. So based on my data, that's what I would have expected. So that's going to be my expected count. Maybe I'll do another one here, and then we'll just fill them in. So let me pick on one more. Maybe I'll look at this, this value, and I'll do, again, the expected count. So I just think, okay, I look at the, I'm doing the column total first. We're going to look at the row total, so I just follow the row that it's in. And I find the column total. And again, I just multiply those. So that's going to be, I'll put it over here. So that's 335 times 390. And again, I divide that by 1,000. And if you compute this, let me see. Let me clean this up. I got this to be equal to, what did I get? I got 130.7. That was the expected count. Let me use the same color. So I got that to be 130.7. And if you go through, you can check my other expected counts. This is 87.8. And then I got 38.3. Again, just by doing the same process. 193.6. So again, nothing complicated, certainly tedious. But again, this is something that, this is why knowing how to use some sort of stats program is so important, or to use your calculator, because you certainly don't want to be doing this stuff by hand. Okay, so now I've got all of those expected counts, and all I'm going to do for each little box is I'm just going to take their difference and square it, and then I'm going to divide it by the expected count. So it says to compute that test statistic. So if I look at, for example, let me look at this first little box. I would take 120 minus 99. I would take 120 minus 99. Again, I need to square that, and I would divide that by 99. And then I would add to that. I would simply go to the next one. So 80 minus 87.8. 80 minus 87.8. Let's square it again over 87.8. And then I would keep doing this. I would keep doing this. I would do it for the next one, 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 the next one. Eventually, I would get down to that last one. So my very last one would be 85. That would be 85 minus 57 squared over 57. And after doing all of that arithmetic, I got this to be equal to 38.004. That's good enough. Okay, so that's my test statistic. This was my value from the table. The moral of the story, if the test statistic is larger than, if your test statistic is larger than that chi-squared of alpha of the degrees of freedom, the idea is we reject the null hypothesis. Well, in this case, we had the test statistic. We computed that to be 38.04, and that's certainly larger than that value we got from the table, which was 9.49. So we reject the null hypothesis, and the conclusion is, if we go back and look at, the conclusion is our alternative hypothesis. Let me just copy that down. So that's going to be it. So again, it's really just a lot of understanding what's happening here. Let me clean this up a little bit. So it's really just understanding. Notice the math wasn't really terrible. Again, you're just looking up the chi-squared value from a table. So, okay, you've got to compute the degrees of freedom. You pick alpha. Just get that from a table. That's not too bad. The observed counts will be given to you. And then you just go and use the little formula to get the expected counts. And then you're just subtracting them, squaring it, dividing by the expected counts, getting that test statistic value, and then just simply comparing that to that value you got in the table. Notice if our test statistic had been less than, if this had been less, we would have kept. If that had happened, if our test statistic had been less, we would have kept the null hypothesis. We would say, oh yeah, it doesn't seem like there is any relationship between the two. But in this case, we definitely had that our test statistic was large, and therefore, we again accept the alternative hypothesis that there is an association between mom's education level and her daughter's feelings about math. So, whew, that was a mouthful. So for those of you that are still out there at this point, good job. I hope this made some sense. I hope it helps you. And yeah, best of luck.